I think quite a few people probably know Adam. Adam is the host of a number of, well, Grant sent out a very nice bio for him. He has an extensive resume, which I'm definitely not going to try and repeat. But many people probably know him from the host of a number of particularly ICOM forums on previously Yahoo groups and now groups.io. He has a fantastic website with all kinds of reports, and so you can get receiver reports on a number of different radios. Again, mostly ICOM, right? You have other radios, but mostly.
Yeah, I cover a couple of non-ICOM products, some SDRs and the ASA Quadra amplifier. All right, so let's get this thing rolling. I gave this presentation originally at the Asia Pacific DX Convention in Osaka in 2016 at the request of MAC JA3 USA, who is the organizer and host of the convention. The convention was going to be held in November of last year, but of course it got cancelled, and I don't know when it'll be held again. Well, there's been a lot of discussion about SDR, meaning just confining the term SDR to the direct sampling SDR, because the homodyne SDR, in other words, the predecessor type of radio which used a pair of IQ mixers in a homodyne receiver configuration. If you go by the ITU definition of an SDR, which I'll cover in the next slide, the homodyne SDR doesn't quite meet that definition because it's got too much non-variable or non-software configurable or non-software variable hardware in it. Okay, so here is the ITU definition of an SDR. A radio transmitter or receiver employing a technology which allows RF operating parameters, including but not limited to frequency range, modulation type, or output power to be set or altered by software, excluding changes to operating parameters which occur during the normal, pre-installed and predetermined operation of a radio according to a system spec or standard. This is very interesting. The ITU took the trouble to actually create a generalized definition of an SDR. So when people start throwing the term SDR around and claiming that a radio like the K3, with all due respect, is an SDR, the part of the K3 which is an SDR is the part between the ADC and the DAC. The rest of it is just a superhead. It's what we call a legacy radio. I use the term legacy in that context. What we'll cover in this presentation, this is generalities. SDR and cognitive radio technology are rapidly displacing legacy radio architecture in critical military, government, and commercial applications. Now, pardon me, there is a case here. We'll cover this. If we consider a direct sampling SDR receiver, it consists of an RF front end, filters and RF amplification, followed by an analog to digital converter, or ADC, which is exposed to either the entire operating range of the receiver or a portion of it determined by a preselector or filter. It converts the RF band into a digital bit stream, which is then selectively down converted in the digital domain by a process called decimation. And the decimation process selects a slice out of the broad, if you like, digitized band, which is equivalent to a superhead selecting a narrow IF out of a broad band of frequencies in the RF domain. The decimated RF bit stream is then subjected to further filtering and processing, and ultimately converted back to an analog signal by an audio digital to analog converter. The ADC has a hard limit in that it clips at a defined power level, as opposed to the superhead, which doesn't really clip, it overloads more or less gracefully. So in designing an SDR, one has to take cognizance of this limitation and manage the gain ahead of the ADC in such a way that the ADC is always kept out of the saturation zone where it goes into the all ones mode or the saturation mode. It can't deliver a digital word any higher than all ones, which is the point at which it clips. Given all of that, there are applications where a legacy receiver is preferable. One example is naval shipboard applications where you have multiple high power HF transmitters in a fairly confined, with their antennas in a fairly confined space, namely on the deck of a ship or on the masts of a ship. You might have a 1 kilowatt transmitting antenna 40 meters away from a receiving antenna. In that case, legacy radio still holds its own. But for many other applications, the direct sampling SDR is much more desirable for the reasons which we will cover in the presentation. Now, there's several OEMs in the amateur world, several new OEMs, as well as a strong open source group, Apache Labs and HPSDR, are building SDR transceivers and receivers rivaling and even surpassing legacy radio equipment. Established manufacturers are transitioning from legacy to SDR. The one OEM which has done this to the fullest extent possible is ICOM. They've really embraced direct sampling, and all their new transceiver models are direct sampling. They've even gone as far as to replace a legacy HF transceiver for the maritime radio services, the M802, with the M803, which is direct sampling. So here we'll explore the relative merits of SDR and legacy radios and the issues peculiar to each type from a radio amateur point of view. We're only going to consider two types of transceiver here: the legacy superhead with a DSP-IF chain behind it, and the direct sampling digital upconversion SDR, in which the receiver consists of an ADC followed by a decimation, digital processing of the decimated signal and demodulation. Transmitter is digitization or digital encoding of the audio, followed by processing in the digital domain, digital upconversion to the operating frequency, and then conversion to analog and RF power amplification. It's assumed that the serious radio amateur will choose either an all DSP radio, all SDR radio rather, or a superhead DSP hybrid radio. As both topologies employ such familiar DSP-based features as noise reduction, noise blanking, notch filters, passband tuning, compression, and so forth, we're not going to discuss these in detail here. Here's a whole slew of abbreviations and acronyms, some of which may be new to you. A DBFS is probably an unfamiliar one. dB relative to full scale. Full scale in an ADC is the clip level. When we test direct sampling SDRs, we frequently drive the signal level applied to the ADC all the way up to 1 dB below clipping, because the ADC will retain its performance right up until you're 1 dB below clipping. As soon as clipping is reached, the ADC stops working because it stops encoding the analog RF signal. DDC is the digital down converter, or DSP we know. DUC is digital up converter. FPGA, field programmable data radio, you guys are probably conceptually familiar with FPGAs. In a lot of the transceivers that are on the amateur market today, a large number of functions are incorporated into the FPGA. In the ICOM 7610, the FPGA even embodies all the functions formerly carried out by a separate DSP chip. An NCO is a numerically controlled oscillator which is a DDS, a direct digital synthesizer with digital output. The output is not converted back to analog and is in fact fed into the decimator, which acts like a digital mixer, a mixer in the digital domain to reduce the operating frequency to a digital pseudo IF, which is then processed. A PIM is passive intermodulation. Very typical example of where you find passive intermodulation is in the ferrite cores of coils in a preselector or bandpass filter. If it's severe enough, passive intermod will really degrade the performance of a receiver. An example was in the ANAN 8000 from Apache Labs. I found it under very strong signal conditions. I found this doing a noise power ratio test. Under very strong signal conditions, noise power ratio took a dive of about 10 dB. So I separated the preselector from the receiver and set up a noise power ratio test with the notch noise generator and the noise receiver. And by hitting the preselector hard, I saw degradation in noise power ratio. Noise power ratio is a test in which you apply a band of noise with a notch in it, and you measure the amount of noise induced in the notch. The purpose of the notch is to prevent the applied noise from hitting the device under test. And then you do all your measurements in that notch. Okay. A legacy superhead with IF level DSP. The DSP chain it's really an SDR in its own right, operating at a fixed frequency. Consists of an ADC, a DSP, and a DAC. The IF demodulator chain and the transmitter modulation process at first IF are replaced by the DSP. So you have a low frequency ADC typically running at 36 or 48 kilohertz. And the signal is, this analog signal is encoded at that frequency, processed, and what comes out the other end is digitized audio, which is converted back to analog audio by a digital to analog converter. And the reverse process takes place in the transmitter. Now, in a direct sampling digital upconversion SDR, the ADC operates at RF. The digital down converter or decimator down converts the RF to a pseudo IF and then ultimately to audio. And in the pseudo IF chain, you have familiar processes of selectivity, things like notch filters, noise blanking, and demodulation take place. What comes out of the demodulator is a digital baseband, which is converted to audio by the DAC. Transmitter audio is the reverse process. The NCO, numerically controlled oscillator, is the equivalent of a VFO in an analog radio. It's tuned to the operating frequency. And these functions, the digital down converter, digital up converter, and NCO are usually incorporated into the FPGA. Now, some designers have been studying the use of a GPU to carry out the functions normally resident in the FPGA. I know that Apache Labs was working on this, and they had a proof of concept project going, but I don't know where they are with it. Right now, the radios that they are producing are architecturally quite similar to any of the other direct sampling SDRs on the market. The RF preselector, preamp, and attenuator, audio chains, and the transmitter RF and PA chain are common elements in both radio architectures. And here are some block diagrams. This one is, the one above is an IC 7600 receiver. You have a bandpass filter, two separate mixers because you have two separate local oscillators. The radio can receive on two different frequencies in the same band at the same time. Then you have a crystal filter known as a roofing filter, which eliminates images caused by the upconversion process from somewhere in the HF band to 64 megahertz. And then you have a second mixer which reduces the frequency from 64 megahertz to 455 kilohertz, where it's filtered again and then mixed down again to 36 kilohertz and presented to the DSP. This is not the 7600, beg your pardon, it's the IC756 Pro series. And this is the transmitter, the corresponding transmitter, where the audio is fed to a DSP board, which incorporates an ADC. What comes out of the DSP is an IF signal, first IF. It's a low 36 kilohertz IF, upconverted to 455 kilohertz, cleaned up by filters, and then upconverted to 64 megahertz, and then down-converted to a frequency in the HF band. The direct sampling SDR has a radical effect on the component count because everything here is replaced by the ADC and the FPGA with or without, either with an integral DSP, in other words, embedded DSP in the FPGA, or a separate DSP. Same thing in the transmitter. Everything from the output of the audio chain to the input of the PA chain is replaced by the digital component, which consists of a transmit chain either in a DSP and FPGA or all in the FPGA, followed by a DAC, digital to analog converter, which in turn drives the RF power amplifier, or the exciter chain in the RF power amplifier. Some of the newer, ICOM embraced a newer architecture originally developed by Rohde and Schwarz, in which the conversion from the first IF from 64 megahertz to the DSP IF is done in one hop by an IQ mixer, otherwise known as an image rejection mixer. If we consider the receiver for a moment, the first mixer converts the RF frequency, the operating frequency, to 64 megahertz, filters to clean it up. This goes into a pair of mixers with both the mixers and the associated local oscillators are each shifted by 90 degrees, which cancels the unwanted sideband or the unwanted mix, and allows a very large conversion step because the image is cancelled by the fact of a very careful balance between the in-phase and quadrature mixers. So what comes out of this is a 36 kilohertz IF, which is then fed to the DSP. A radio which would incorporate this would be, for example, the IC7700. Quite a number of the ICOM models are using this scheme. Started with the 7800, then the 7700, the 7851. And a couple of their other models, including the 7600, have a modified version of this. This is a simplified block diagram of one of the flex radios. Again, we have two receivers known as spectral capture units, each with bandpass filters, a preamp, an attenuator, an ADC. All this information, the digital information derived from these receiver chains, is presented to a high-speed DSP, and I think it's a 1.4 gigahertz CPU and DSP, and the output goes to via another DSP to the Ethernet, and then to a computer. The computer program running in the Ethernet in the associated PC, namely the smart SDR, gives complete management of the transceiver. In addition to the Ethernet link to the computer, there's an audio DSP and a codec, which is a combined analog to digital and digital to analog converter operating at audio frequency, which drives the speaker and takes the signal from the mic. The issue here is that the radio is tethered to a PC, and unless it's the M series of flex transceiver, which has the Maestro control panel. The Maestro control panel is actually a highly modified Dell tablet. You're always tethered to a PC. With the ICOM radios, the radio's standalone SDR. In other words, its front panel will allow you to run it. You don't need a PC, although I think the majority of operators nowadays have a PC associated with the radio and seem to use the PC exclusively to run the radio. The poor front panel never gets touched even. I prefer to operate the radio from its front panel. So here we have a situation where the computer just provides a control surface and the audio is done separately by the codec and DSP, which are on their own little board. There's another approach to the computer tethered SDR, in which the FPGA is linked directly. Oh yeah, this is an FPGA which has a high power DSP in it. The FPGA is linked via Ethernet to a PC which has in it audio codecs. So the audio interface to the radio is done via the PC. In the flex radios, you have the option, you can have either your audio either through the PC or direct through the radio. And with a radio such as the Apache Lab series, the Anand series, the Power SDR software and its derivatives do much more in terms of signal processing than is done in the flex, where signal processing is done mainly inside the radio itself. Now, I referred earlier to a standalone SDR transceiver. Let's take a look at the IC7300. What we have here is an attenuator, an RF amplifier, which I haven't shown, the ADC, and then what amounts to a digital version or a digital domain version of the image reject mixer with its in-phase and quadrature local oscillators. But all this, we must visualize, try to visualize it as being in the digital domain. It puts out a digital IF, which goes into the DSP chip, and is ultimately converted to audio. And the DSP also generates a DC voltage for AGC. And the AGC is different from that in a legacy type receiver, because what it does is it varies the loss of an attenuator in the front end. Now, in a radio with an ADC, the optimum operating point for this receiver, for a direct sampling receiver, is to set the gain between the antenna and the ADC such that the band noise is right at the noise floor of the receiver, perhaps a dB or so above the receiver noise floor. So on 40 meters, when you have all that band noise, you can see it on the screen or the S meter of your 7300 or 7610 or similar. You adjust the RF gain control, or in the 7610, you have a variable step attenuator. You set the attenuation so that the band noise is just at the threshold of the scope or waterfall, or that the S meter just registers it. The idea there is you don't want band noise to activate the AGC. You want to keep the receiver dynamic range for signals. If you reduce the gain ahead of the ADC such as to diminish the impact of the band noise, you don't care about the band noise because any signals that are in the band noise are lost anyway, because the band noise will wipe them out. I have an article on my website entitled Gain Management in a Direct Sampling SDR, which covers this. And here's the what goes on in the FPGA of the 7300. This is the transmitter side. Microphone amplifier, an analog to digital converter, band pass filter, the digital modulator, which produces a 36 kilohertz rather, pseudo IF in the digital domain, and this goes into the FPGA chip. Okay, there's a DSP chip and an FPGA chip in the 7300. The 7610 does all this in the FPGA. Again, the FPGA uses an up-converting image reject mixer in the digital domain to produce an RF signal, which is converted back to analog, filtered and amplified, and that's what goes out over the air. So it greatly reduces the component count in the transceiver and also the cost. We cover this here, the architectural advantages. Block diagram and signal paths are dramatically simplified. You get rid of mixers, analog local oscillators, and by so doing, you get rid of IMD noise, spurs, and images in the mixers, and phase noise and reciprocal mixing in the local oscillators, and spurious signals as well. The reciprocal mixing in a direct sampling SDR is far lower, or the reciprocal mixing dynamic range, which is the difference between the level at which a predefined amount of noise occurs and the receiver noise floor, is far higher than for most legacy receivers. IF roofing filters disappear, and with them passive IMD and phase distortion, filter insertion loss, and IF leakage. All those go away. But you need an anti-aliasing filter, which is a low-pass filter at the output of the RF chain before you go into the ADC. There you want to prevent signals which are on the other side of the Nyquist frequency, half the sampling rate of the ADC, from producing in-band artifacts. An example is, your sampling rate is, let's think of an easy one here. Your sampling rate is 80 megahertz, and you're listening to a signal, let me see if I get this right, at 50 megahertz, then a spurious signal at 110 megahertz will show up in the receiver as if it were at 80 megahertz. It's like an image, and the anti-aliasing filter suppresses that. All these radios have an anti-aliasing filter. the payload signal is digitized at the earliest stage. Signal management is done entirely in the digital domain. What's very important is that between the ADC and the DAC, there's no added noise or distortion. Software-defined signal processing greatly facilitates the addition of new modes, protocols, and features, and so forth. Customization to meet the needs of different user communities is cost-effective, and a process called dithering reduces the ADC intermod, the intermodulation in the ADC itself, at a very slight cost in noise floor. What dithering is the deliberate insertion of a pseudo-noise signal into the ADC. The signal is then removed after digitization. What it does is it decorrelates IMD products into noise, and the noise has only a fairly slight impact on the noise floor of the receiver. Dithering is a function within the ADC itself. The majority of the ADCs available on the market today have a dithering mode which can be turned on and off. One ADC, which is quite well known, it's an analog device, is AD9467, used by Flex, doesn't have dithering. So Flex has to have a process of external, well, dithering external to the ADC. I don't know how it works, and they don't describe it. They call it magic knobs. But all the ICOM radios, with the exception of the IC705, have dithering, which can be switched in and out. So does the Anam series and a number of others. Maintenance is very much simpler. Hardware alignment points are almost non-existent. Adjustment and calibration parameters can be accessed via menu, and interfaces to other equipment are easily configurable. Component counts are greatly reduced. Cabinet size is smaller, weight is lower, number of boards is lower. Reliability and cost reduction are, reliability improvement and cost reduction are also significant factors, and there's a potential reduction in standby power consumption. Now, dynamic range considerations. This is something that's much talked about because of the, let's call it the preoccupation in some areas of the amateur community with dynamic range. The ADC clip level, that is the input level at which the output is all ones, as we've covered before, sets an absolute limit on the signal level which can be applied to the input. The ADC stops working at the clip point. Typically, the ADC clip level measured at the antenna input is -3 dBm. It's in the range -3 to -10 dBm. The ADC is exposed to all RF signals in the passband. The passband width is limited by the preselector or bandpass filters, which can be switched out in some designs for wideband reception. Some low-end SDRs don't have a preselector. The IC7610 has 2 preselectors in cascade, a tracking single pole preselector with 1 tuned circuit, followed by group bandpass filters. Each bandpass filter is typically a couple of megahertz wide and is selected when a band is selected. If all the applied signals were equal in amplitude and phase, the clip level would decrease by 10 log the number of signals. So for 64 signals, it would decrease by 21 dBm. It would decrease. See if I can get this out of the way here. By 21 dB for 64 signals. Statistically, though, this is seldom the case. If you have a large number of signals, it will not occur very often that all the signals are simultaneously at either positive peak maximum or negative peak maximum. This is why a receiver with an ADC works as well as it does. The input power limit imposed by ADC clipping requires a different approach to AGC design. The AGC in a legacy receiver provides for averaging audio output over a wide range of RF input level to prevents overload of downstream mixers and IF stages. In a direct sampling SDR, the AGC can also adjust the input level to the ADC with the voltage controlled RF attenuator to keep the ADC below clip level. So in a radio like the 7300, the RF gain control varies the insertion loss of an RF attenuator in the receiver's RF chain ahead of the ADC. This attenuator is also controlled by the AGC line. So you can set the RF gain control, and if the signal exceeds the AGC threshold, it will increase the attenuation further. The 7610 has that and also has a manual step attenuator. So you can select the level at which the ADC operates. Many SDRs have a clip indicator in the form of an overflow indicator which lights up, or a light which comes on to inform the operator that the ADC is going into clipping. The flex radios don't have that. Strong signals outside the detection channel or receiver passband, equivalent to the IF, can drive the ADC into clipping. As I said here, the operator can also set the ADC input level via the manual RF gain control. If the front end has sufficient gain reserve, you won't lose too much sensitivity. Now, there's one SDR design used by Collins in an airborne HF SSB transceiver, which has two AGC loops, one in channel and one out of channel. The in channel AGC loop varies the gain of the there are two cascaded RF amplifiers. The in channel varies the gain of the first stage. The out of channel varies the gain of the second stage. The idea is that a strong out of channel signal shouldn't degrade the receiver noise figure by putting a lot of attenuation right in front of the RF amplifier. And this is the Collins receiver front end. These are the front end filters. There's an attenuator here, RF amplifier. This attenuator controls the gain of that RF amplifier. And this is the in-channel AGC. If you have a strong signal in the passband of the receiver, or in the channel as I call it here, you don't mind if you degrade the noise figure. But if you have a strong out-of-band signal, you don't want to hurt the noise figure of the receiver. So you don't degrade, you don't lower the gain here. You lower the gain here to protect the ADC. This is a Collins patent, which is apparently working quite well. I've got a little calculation here. What you call the magic of process gain. Expressing it very roughly, if an ADC was noiseless, its dynamic range would be 16 times 6 dB, roughly 96.8, roughly 96 dB. But real-world ADCs have finite noise floor, which from that you can calculate a parameter called ENOB, or effective number of bits, which works out to 12.7 effective bits for a 16-bit, a typical 16-bit ADC. Slightly less for a 14-bit ADC. The 7610 and the Collins radio use a 16-bit ADC. 7300 uses a 14-bit. The Anon uses a 16-bit. The Flex radios use a 16-bit. Well, 78 dB doesn't really look all that great, but if you reduce the bandwidth from, say, that of the RF preselector to that of a typical audio channel, namely from a couple of megahertz to 3 kilohertz or so, you get a scaling factor which is quite large. And the process gain in this example that I've cited here is 51 dB. That means that your instantaneous dynamic range is 129 dB, which is quite respectable. Of course, if all the applied signals are of equal amplitude and in phase, this will fall apart. But as I said earlier, in practice, this never happens. A lot of people criticize the concept of process gain by saying it's not for real, but it does. Process gain is valid because not all the signals applied to the ADC are of equal strength and in phase. In fact, that almost never occurs. Here's a short discussion of MDS, IMD, and dither. There's a chip ahead of the ADC is a differential ADC driver. It's a push-pull amplifier. Typically, it has 8 dB noise figure and about 20 dB gain. You can add a low noise RF preamp ahead of it for higher bands, 21 megahertz and above. Now, we've discussed dithering already. Dithering actually breaks the coherent or correlated IMD products into decorrelated signals, in other words, noise. So what you're doing is you're converting IMD into noise at a level which is not high enough to degrade the noise performance of the system. And you can switch dither on and off too in many of these radios. Here's an example of a spectrum scope. Many SDR receivers used in the amateur field and also for surveillance, intercept, and for shortwave listening have a built-in spectrum scope. It's an FFT or fast Fourier transform scope, which can sample an entire band in one operation. The y-axis is derived from the ADC digital output and is inherently accurate. You can calibrate your scale, your spectrum scope scale and your S-meter scale directly in dBm, and they'll be accurate. The x-axis is derived from the numerically controlled oscillator to ensure frequency accuracy. This is a two-tone test. The IMD products are buried in the noise there. A waterfall is an XYZ axis display. Again, it derived from the spectrum scope. X is frequency, Y is time, and Z is amplitude. So the waterfall trace changes color and brightness with increasing amplitude, as we see here. Many of the SDR radios have a waterfall as well as a scope. So you can keep them both turned on, and this will enable you to get a good picture of the signal. You sometimes hear of latency. Latency is the combined delay between an input or command and the desired output. It takes time for a signal to cross a receiver or transmitter and be processed within the various processing chains. The transit time from the input, which can be in a receiver is the antenna, and the transmitter is the audio or keying source, to the output, that is defined as the latency. Contributors to latency include active circuits and filters in the signal path. In a purely analog radio, crystal or mechanical filters are the largest contributors. Still, the total latency is 1 to 2 milliseconds or less. In the legacy radio with IF level DSP, the transit time across the DSP is the longest component, delay component. Latency can be no more than about 15 to 20 milliseconds. Direct sampling SDRs are the worst offenders in terms of latency. They can have from less than 5 milliseconds to more than 400 milliseconds. The flex radios have 160 to 165 milliseconds latency on receive, which is dreadful for CW operation. The Apache Labs Anon series has successfully addressed this problem by developing filters optimized for lowest latency, which can reduce the latency dramatically. I think I've got a curve in this presentation that shows that. The 7300 doesn't have much latency, 3.7 to 15 milliseconds. The highest values occur with narrow DSP filters. And 4 milliseconds latency on transmit. That is really not bad. How to mitigate latency. You have to strike a compromise between filter shape factor and latency. And what's shape factor? Shape factor is the ratio between the 3 dB bandwidth and the 60 dB bandwidth of the filter. The OpenHP SDR group has done remarkable strides in this area thanks to Warren Pratt, NR0V. Warren has designed filters which reduce the receive latency to less than 20 milliseconds, which is very important if you're working CW or some of the digital modes. DSP transit time also contributes to latency. This aspect can be addressed by code optimization and use of a fast DSP or computer. Here's the curve I wanted to show you. The blue line is the low latency filter. Less than 20 milliseconds across a wide range of filter shape factors. And this is the linear phase filter, where latency increases dramatically with falling shape factor. And this is the default curve for the Power SDR version 3.3.7, which was an earlier version when this that was current when this presentation was put together. Now let's think about the transmitter. The audio or baseband signal leaving the audio ADC or codec remains in the digital domain until it leaves the DAC as RF drive to the PA chain. So the whole signal processing function in the transmitter adds no noise or distortion to the signal, which is a huge advantage over any analog design. As the ADC and DAC clocks are the primary phase noise contributors, a design with low phase noise clocks can almost eliminate transmitted phase noise from the transmitted signal. The removal of mixers and local oscillators eliminates spurious signals and phase noise from these sources. Transmit latency in CW can be greatly reduced by keying the carrier in the FPGA rather than in the DSP. Flex does that. I'm not sure if Apache Labs do yet. Analog IF filters with their potential for phase distortion are completely eliminated. The exciter topology facilitates the inclusion of high power amplifier linearization, such as adaptive pre-distortion. The example of that is the Apache Labs Pure Signal, which is a feedback loop where a sample of the output signal from the PA is taken back to an early stage in the exciter Oh, pardon me. Hey, hey, Walter, I'm on a Zoom meeting. Can I call you back? You absolutely can. Bye. Sorry about that. Okay, where were we at? Yeah. Sorry, I want to see this. Yeah, we were talking about the transmitter. Phase noise is a big thing in transmitters now. Well, there are two factors to transmitter noise. There's composite noise and there is phase noise. Well, there's composite noise, which is a combination of phase and amplitude noise. Phase noise is generated by the frequency generation process caused by phase jitter in oscillators, and the equivalent in the digital domain, which is jitter caused by uncertainty in digital to analog converters. Amplitude noise is caused by shot noise in the exciter chain, which is basically a chain of power amplifiers. Another important source of phase noise in an SDR is the clock. If the clock oscillator has severe phase noise, and or if the clock distribution, which is the clock generator and amplifiers following the crystal oscillator, are not properly laid out, this can create a severe phase noise problem. We had that with the early Apache Labs ANAN, where the layout of the clock distribution scheme was improper, and as a result, when dither was switched in the receiver, the phase noise became so severe that it degraded the noise floor by about 10 dB. And Apache Labs fixed that by choosing a different clock oscillator and laying out the clock distribution tracks on the board more carefully. The IC7300 had a similar problem in the early days, and they fixed that by changing the layout of the board traces around the ADC and the clock generator. So that's absolutely critical. Amplitude noise, the best way to fix that, again, is careful choice of components and making sure that you run the components well within their ratings, proper decoupling of power supplies and control lines. And it takes quite a lot of work to clean up amplitude noise. Although in practice, amplitude noise is lower than phase noise. But there has been a lot of criticism of some of the current amateur transceivers because, especially at fairly large offsets, a couple of 100 kilohertz removed from the carrier or from the operating frequency, the phase noise and amplitude noise is sufficiently severe to cause noticeable interference. A lot has been done to improve receivers, but the transmitter and noise improvement is still a work in progress. And unfortunately, measuring instruments for measuring phase noise are still very expensive and exotic. Although you can do remarkably well with a phase noise measuring, with an SDR receiver such as the Perseus has a phase noise measuring device because it has very low inherent phase noise. The removal of mixers and local oscillators improves matters in this area considerably. As we've covered before, transmit latency in CW mode can be reduced by keying the carrier in the FPGA rather than in the DSP or in the external PC. Analog IF filters are gone. Linearization becomes feasible, where feedback from the output of the power amplifier is fed back into or combined in antiphase with the signal at the output of the ADC after suitable processing. This has the effect of cancelling the intermod products and can improve the overall IND performance of the transmitter by up to 30 dB. The parts count of the DUC transmitter is much lower than that of most legacy transmitters. And of course, there are many fewer alignment points. Operational features of an SDR. What bells and whistles do you get with an SDR? A wideband FFT spectrum scope. You can set it to display either a narrow segment, an entire band, or the full RF bandwidth of the receiver, for which you need to bypass the preselector. Some SDRs have two independent front ends, each with its own preselector and gain management tools, support diversity reception, wide or crossband split, and even full duplex operation. The IC7610 has two completely independent receivers, each with its own tracking preselector. And the two receivers, the clock sources of the two receivers are coherent, so the receivers will be in phase when they're switched into diversity mode, which allows one tuning knob to tune both receivers simultaneously. Another benefit we get is SDR implementations with an Ethernet baseband interface to a PC, which allow addition of new modes, experimental signal processing, development of virtual interfaces to popular software, such as contesting and logging programs. Another feature available on some of the radios is NTP time server compatibility, where the radio's internal real-time clock can be synchronized to an NTP time server. Although an SDR, which is a standalone or uses the PC only as a control surface, is essentially a closed system, many of these designs also allow virtual connections to amateur radio software. Direct sampling SDRs perform best with gain management, as we discussed earlier, based on a good understanding of the relationship between signal strength, band noise, and MDS. Excuse me. The IC7610 has a 1 megahertz wide IQ channel output from the receiver, which can be used to feed an external software program such as HDSDR, which will present a much more detailed spectrum scope than the one in the radio, and also allow control of the frequency and other parameters from the PC running HDSDR. There are a couple of other programs which will operate correctly with the IQ port. I believe DX Lab, Win for ICOM Suite, and SDR Sharp can be made to interface with the 7610 using an external IO DLL program. So we ask ourselves, which is better, an SDR or a legacy radio? You can't really say one's better than the other. It's a question of application and needs. The individual operator's specific needs will determine the response to this question. There's no one-size-fits-all answer. SDR can offer clear advantages over legacy architecture in terms of overall performance, design simplicity, versatility, reliability, and cost. Nonetheless, some top-ranking legacy HF transceivers perform superbly in brutal RF environments, both in amateur service and in demanding military, government, and commercial usage. An example being the Rohde and Schwarz line of HF transceivers. The only thing is you pay 6 figures for one of those. In choosing between an SDR requiring a PC or a standalone knobbed SDR, I think the guide is personal preference. Radio amateurs who have been comfortable with legacy radios may find that a standalone SDR meets their needs whilst providing a refreshing uptick in performance and capability. And here are a few references. The link to this presentation can be found on my website, ab40j.com.